Okay, hello everyone. My name is Sue.
My name is Audrey.
Yeah, and today we're going to present our project on that trains the CNN to classify chest X-rays as either normal or pneumonia using 3000 grayscale images at 96 by 96 pixels for our ENGRI project. Yeah, so to give a little bit of context for this problem, it actually looks a little bit harder than it sounds. And first of all, we have a pretty low resolution picture that forces the model to work from abstract textures, and a normal anatomy looks very identical to a pneumonia infiltrate. And this could lead to problems like false negatives, which are misdiagnosis, which could cause a lot of harm in clinical settings. And then moving on to our baseline model uses a single convolution block of 16 filters, max pooling, and a 64 unit dense layer. And this got us a 91.78% test accuracy, which is pretty good. But looking at the validation loss, it spiked after the 10th trial while the training kept falling, which showed a lot of overfitting, and the one convolution layer simply wasn't enough to capture a lot of subtle pneumonia patterns, as we can see in this graph. And then this led us to our first early custom model. And for this, we widened the single convolution block to 64 filters, expanded the dense layer to 128 units with no depth increase or regularization. And for this model, the training accuracy actually shot to about 99%, while validation barely moved. And this showed a very good version of high variance, where the model had enough capacity to memorize every training image, but it learned a lot of noise instead of generalizable patterns, and was a pretty big failure on our part. And then, as you guys can see in this model or in the graphs for this, the training loss collapses to nearly zero, while the validation loss was flat, showing a overfitting model. And then next, I'll be passing on to Audrey.
So our best model makes three really important changes. First, we deepen the network to three convolutional blocks with 32, 64, and 64 filters. Second, we use a 5 by 5 kernel on the first layer, which creates a white lens that captures broad opacities in its first pass, while the 3 by 3 kernels that follow refine the fine details. Third, we add out regularization and reduce the learning rate to 0.001, training for 45 epochs. The result is really promising. Test accuracy improved to 94.44%, with a much healthier train validation gap. Now let's see some graphs for the final custom models. Unlike the earlier models, training and validation loss descend together and stabilize really smoothly around the same value by the final epochs. Accuracy curves track closely throughout all 45 epochs, no divergence and no overfitting spec. The confusion matrix also shows predictions concentrated really firmly on the diagonal. After all these experiments, we did a comparative analysis. The comparison table summarizes the full progression. The baseline underfitted, the early custom model overfitted. Only the final model achieved genuine generalization, cutting the gap down to 1.5 while improving test accuracy by 2.66 points. We have two takeaways for this project. First, deeper feature extraction worked better than simply making the network wider in this case. Using multiple convolutional blocks helped the model learn more useful patterns in the X-rays, instead of only capturing very basic features. Second, regularization was essential. Once we increased the model size, weight decay and a lower learning rate were what kept it from overfitting and allowed the extra capacity to actually help. So that's all for today. Thank you.
Thank you so much.